In our last videos, we covered FPS's installation, navigation, and data collection capabilities. Now we're focusing on FPS's powerful splicer control and fiber shaping modules, giving you complete control over your splicer's operations. The first module in the splicer control category is the live video module. This allows you to stream the splicer's screen images and interact with the splicer via the virtual keypads on either side of the screen displays. Using the live video module is simple and straightforward. To start the video stream, click the green play button, and to stop the stream, click stop. Depending on the orientation of the splicer's screens, the video might display upside down at first, but this is normal and can easily be fixed by selecting the rotation checkbox. If you need to capture an image of the current splicer display, click Screen Cap. To save it, select Save Screen Cap and choose your storage location. Next, we'll dive into the Power Meter Reader module, a crucial tool for fibers that have shapes or structures preventing side view core alignment. FPS currently supports the following power meters: the AFL OPM5, the Thorlabs PM100D, Thorlabs PM100 USB, Thorlabs PM400, and the Newport 1830R. Other power meters can be accommodated on request. Once your power meter is connected, select it from the power meter menu. The AFL OPM5 is the default, but once connected, your power meter should be selected. Click Start Stream to begin pulling data from the power meter. Use Set Reference to establish a baseline power reference, and then select Active Align to initiate the active XY alignment process. Parabolic alignment works similarly to active alignment, but instead of scanning in even step increments, it utilizes a two-pass method to find the best alignment position. First, the rough pass identifies the general core vicinity. Then the fine pass uses smaller step sizes to find the absolute best alignment position. By default, rough and fine steps are set to 3 microns and 1 micron respectively, but these values can be adjusted in the Step L and Step F boxes. Depending on your power meter settings, loss measurement may appear as a positive or negative number. If the power meter shows a positive number, select the min radio button so the system looks for the smallest positive value. If the power meter displays a negative number, select max to accommodate a sign change. Next up is the manual control module, which allows you to manually adjust Z, theta, and XY motors, but only when the splicer is in the ready, finish, or pause state. There are 3 ways to move a motor. Type a desired position value into the text box next to each motor, drag the slider with your cursor, or click and hold the arrow buttons for fine-tuned movement. If you adjust the motors using the splicer keys, click Refresh Positions to sync the updated position data into FPS. At the bottom of the page, you'll find motor movement speed options. Selecting Fast moves motors quickly but reduces precision, while selecting Slow moves them at the lowest speed, retaining maximum precision. Under the Theta Motors section, selecting Spin Stop starts or stops the rotation motors. Selecting Go Home resets the Theta motors to their default position. For the arc or laze function, input a duration in seconds and a power level in bits, then press Fire to initiate the process. To cancel an active arc or laze sequence, simply press Stop Arc. The Command Sender module allows you to manually execute FPS API commands with the splicer. To test a command, enter the preamble character followed by the command string. For example, typing $reset and pressing Enter sends a reset command to the splicer. If the command is received successfully, FPS will return ACK, indicating command acknowledgement. If unsuccessful, it will return NAK, meaning the command could not be processed or was not acknowledged. The first of the fiber shaping modules is the ball lens module. This function allows you to create a lens on the end of a fiber using the glass's natural tendency to self-adhere when in a molten state. This is often referred to as the matchstick effect. By firing the arc and slowly driving the fiber into the laser or plasma field, we can form a precise lens. The size and position of the ball lens depends on 3 primary factors: the arc or lasing power, the Z motor feed rate, and the fiber's cladding diameter. Each of these settings can be adjusted to fine-tune the lens characteristics. In the dimensions field, you'll input the diameter of the fiber being used along with the ball parameters desired. If the ball lens is part of an end cap, you'll almost always need to splice first, especially if the end cap diameter differs from your primary fiber. If you do need to splice first, you'll set the splice offset value, which determines how far from the splice the center of the ball should be. This helps compensate for overlap during splicing and allows fine-tuned position of the lens relative to the splice point. Below the input boxes, you'll select which splice mode to write your ball lens program to, and if you're splicing first, which splice mode to use for that process. FPS will also calculate the cleave length for each fiber. This is critical because the tip of the fiber should be positioned at the edge of the screen for proper lens formation and image processing. If the length is incorrect, adjust the stripping and cleaving settings until your fiber is properly seated in the figures. The heating section determines how much power is applied to the fiber during lens formation. Preheat time softens the glass before feeding begins. Absolute power is the splicer's current standard arc or laze calibration value, and relative power adjusts the standard power to fine-tune the heat level. To check the splicer's current calibration, click Get Calibration Value. For example, if the standard power is 265 bits, but that's too powerful, you can set a relative power of minus 30 bits to reduce the heating intensity. This adjustment is reflected in the splicer display as standard 265-bit minus 30. Break add power sets the additional power level required when splicing before lens formation. This process splices the fiber, then burns it apart at a precise location, leaving exactly the right amount of material for lens formation. If the break add power is too low, you may see a late separation or an incomplete separation, leading to deformation or poor lens quality. The movement and rotation controls section allows for additional adjustments. For larger lenses, it's recommended to heat with rotation to minimize drooping due to gravity. Feeding speed also plays a role, because if the feeding speed is too high, the neck region of the lens will be heated and you'll see greater axial offset from the fiber's center. At the bottom of the ball lens module, you'll find the main control buttons. Initiate moves the splicer into position to start the lens process. Start begins the ball lens formation. Stop interrupts the process if needed, and Measure analyzes the lens characteristics after being made. For FSM 100 users, selecting real-time control allows the splicer to finish the ball, measure the results, and adjust and retry up to 10 times until the lens reaches the target diameter. This ensures that the final lens dimensions match the required specifications. The next module under fiber shaping is the taper module. This function allows us to create tapered fibers by systematically adjusting fiber diameter, taper lengths, waist length, and taper shapes. The taper module landing page is where you define the fundamental design parameters for the taper you want to create. To begin, input the following: the fiber diameter, the tapered waist diameter, taper lengths, waist length, and taper shape. At the bottom of the page, you'll see the taper control buttons. Initiate moves the motors to their starting position. XY alignment aligns the fiber axially. Taper executes the tapering function, and Measure verifies the results against the target design. These controls remain visible across all pages of the taper module. The movement page is where you'll fine-tune the taper settings. In some cases, the starting parameters may be close to what you need, while other times some tinkering is required. There are three key sections to this page: taper movement, heating parameters, and rotation settings. At the top, you'll see an illustration of the taper. While no values appear here, the arrows indicate the fiber's movement direction during tapering. To change the tapering direction, select Reverse Tapering. Next, choose either Auto Pulling, which is where the splicer calculates feeding speed automatically, or Auto Feeding, which is where the splicer calculates the pulling speed automatically. Based on the input dimensions, the motor movement boxes will populate with calculated values. These boxes will remain green unless the taper exceeds the mechanical limits of the splicer. For FSM 100 users, you have the option to use the sweep motor for extended range of motion, although this does reduce precision. To apply pre-taper tension before heating, check the pre-taper tension box and enter the desired movement distance. If precise movements are required, selecting the backlash correct resets the motors, compensating for any free play of the system. Just like the ball lens module, the tapering module uses a preheat time, an absolute power, and a relative power. Instead of brake add power, this module features waste add power. This fine-tunes the power level applied during the tapering process, ensuring the fiber reaches the target diameter smoothly. The warm taper image function captures live thermal feedback during tapering. You can turn WTI off, monitor tapering progress, and actively control the tapering process. Since some fibers display very strong WTI images, while others are too dark, the WTI controls allow you to adjust the thermal contrast for optimal visibility. Once the tapering process is complete, switch over to the Measurement tab. Here you'll see a graph comparing the measured taper against the original design parameters. Use the adjustment controls to refine the measurement speed, graphical overlays, or fine-tuning for accuracy. Once satisfied with the results, click Create Report to generate a Microsoft Excel file containing a taper graph, design and measurement data, and key parameters used in the process. This will serve as documentation for future reference. The final step is the Review and Upload page. This provides a quick summary of all tapering parameters. Before uploading to the splicer, confirm that no restricted functions are selected. Restricted functions include auto-feeding movement, sinusoidal taper shapes, and WTI-controlled tapering. If you're uploading the mode to a splicer, decide if splicing should occur first. For most cases where a single window strip fiber is needed, splicing is not necessary. Otherwise, you'll see the notation XY align mode number change to splice mode number. From here, select the splice mode you'd like to use and choose which mode slot the taper function will occupy. Once ready, click Upload Taper Module. Now, simply load your fiber into the splicer and press Go to execute the taper function. The taper module provides powerful tools for creating precise controlled fiber tapers. With proper adjustments to movement speed, heating power, and warm taper imaging, you can fine-tune your tapers for optimal performance. Now, let's move on to the final fiber shaping function, the Parabolic Taper module. The Parabolic Taper module functions similarly to the standard tapering function, but uses a different methodology to create a parabolic fiber shape. Unlike standard tapering, which pulls a fiber in a linear motion, this method sweeps back and forth repeatedly over a single fiber section until the target diameter is reached. This module requires fewer input parameters. Delta speed, which is the difference in movement speed between the ZL and ZR motors, waist diameter and length, measurement speed, diameter step settings, and relative power settings. Smaller delta speed values increase accuracy, but also require more time for the taper to complete. Once the parameters are set, you can initiate the motor positions, start the tapering process, and measure the final product. If satisfied with the results, you can upload the taper mode, select a splice mode if applicable, and execute the function directly on the splicer. With FPS, you have full control over your splicer and access to advanced fiber shaping tools to optimize performance. This concludes our FPS video series. Thank you for watching, and as always, AFL is here to support your fiber processing needs.